Antimicrobial drugs are, without a doubt, one of the greatest things to ever happen to modern medicine. Seriously. They've saved an incredible number of lives and made things we totally take for granted, like major surgery, even possible. But this miracle, it's starting to break. And the very tool we created to save us is now facing a threat of its own making.
So that's really the heart of it, isn't it? On one side, you have this incredible medical miracle, but on the other, you have this growing shadow of antimicrobial resistance. Let's really dig into this double-edged sword. And look, this isn't some problem for the distant future. This is happening right now. According to the CDC, this number, over 23,000, that's the minimum number of people who die in the United States every single year from infections that are resistant to antibiotics. We call them superbugs. It's a pretty staggering number when you think about it. To really get a handle on the danger we're in now, you've got to appreciate just how amazing these drugs were to begin with. Penicillin, the first big one, was a complete game changer, especially around World War II. It literally turned infections that were once a death sentence into something you could actually treat. So that brings us to the big question we're tackling in this explainer. How on earth did we get here? How did this powerful tool, this thing designed to save us, start creating enemies that are even tougher to beat? Well, let's find out.
Okay, so how did these drugs actually work? I mean, what's their secret? To understand why they're failing, we first need to take a look inside our microbial arsenal and see how they were designed to win the fight. The entire idea, the genius behind it all, is something called selective toxicity. You can think of it like a magic bullet. The goal is to create a drug that can hunt down and destroy an invading microbe without causing a bunch of collateral damage to our own cells. And this works because, thankfully, our cells and bacterial cells are built very, very different. And this slide right here shows us exactly what those differences are, all the places those magic bullets can aim. You can see all these unique parts of the bacterial cell. We can attack its outer wall, something our cells don't even have. We can mess with how it builds DNA and RNA. We can even jam up its little protein factories. Each of these is a weak spot, a vulnerability that we can exploit.
So one of the most common ways to do this is by going after that bacterial cell wall. Like I said, our cells don't have one, so it's a perfect target. A drug like penicillin basically works by sabotaging the construction crew. It blocks the enzyme that builds the wall, so the wall never gets finished. And without that protective armor, the bacterium is just too fragile and it basically bursts. Another really clever strategy is to shut down the bacterium's protein factory, which is called a ribosome. Now, we have ribosomes too, but the bacterial ones are just different enough that drugs like tetracycline can get in there, bind to them, and just jam up the whole assembly line. If the bacterium can't make proteins, it can't grow, it can't reproduce, it's just a dead end. But, and this is a huge but, microbes are not just sitting there waiting to be attacked. They've been evolving for billions of years. So for every single weapon we've come up with, they have worked to evolve a counterdefense. This right here is where the real arms race begins. So you can really think about it like this. On one side, you've got a susceptible bacterium. It's an open target. The drug gets in, does its job, game over. But on the other side, a resistant bacterium is like a fortress. It's got active defenses up and running to block the drug, destroy it, or just kick it out. And this slide gives us a peek into the bacteria's pretty impressive survival toolkit. You can see a few different strategies right here. Pumps that shoot the drug out, or tools that change the target so the drug can't find it. We're going to break down 3 of the most common ways they fight back. Okay, first up, some bacteria have basically installed bouncers at the door. They're called efflux pumps. And as soon as an antibiotic molecule dares to come inside, these pumps grab it and physically throw it right back out before it can do any damage. Pretty clever, right? All right, next strategy. If the drug is designed like a key to fit a specific lock, well, the bacterium can just change the lock. A tiny little mutation can change the shape of the target just enough so that our drug, our key, no longer fits. It just bounces right off, completely harmless. And then there's maybe the most direct approach of all. Just fight fire with fire. Some bacteria produce their own weapon, an enzyme that literally hunts down and destroys our antibiotic. The classic example is an enzyme that seeks out penicillin, finds a critical piece of its structure, and just breaks it. And just like that, our wonder drug is totally useless. Now, this bacterial evolution isn't just happening in a lab somewhere. In fact, our own actions are basically pouring gasoline on the fire. We are creating the absolute perfect conditions for these resistant superbugs to evolve, thrive, and spread. Check out this chart. It tells such a powerful story about the pressure to overprescribe. What you're seeing is that over about 13 years, the number of parents who expected or even demanded an antibiotic prescription for their kid went up a lot. And that demand, it fuels unnecessary use, which is a massive driver of resistance. And here's the crucial thing. It's not just overuse, it's also misuse. So on one hand, if you don't finish your full prescription, you kill off all the weak bacteria, but you leave the strongest, toughest ones behind to multiply. And on the other hand, using an antibiotic for a virus, like the common cold, it does absolutely nothing to the virus, but it still gives all the bacteria in your body a chance to train against the drug and evolve their defenses. And there's another hidden danger. Using what we call broad-spectrum antibiotics can be like carpet bombing your body's ecosystem of good bacteria. As you can see here, when you wipe out all those helpful microbes that are normally protecting you, you can clear the way for a really dangerous, drug-resistant pathogen to move in and take over. And that leads to a whole new, and often much worse, superinfection. So all of this brings us right up to today. We are now facing the direct consequences of this evolutionary pressure we've been applying for decades. And honestly, the challenge ahead is huge. It is so important to understand that this is an ongoing arms race. This isn't a single battle we can win and then just declare victory. It's a constant struggle where we have to keep innovating just to stay one step ahead of an enemy that literally never, ever stops adapting. And the result of this whole arms race? The rise of these superbugs. These are the microbes that have collected a whole bunch of different resistance tricks. So they're not just resistant to one drug, but to many different kinds of drugs. They're the ones that can escape almost everything in our arsenal. And that leaves us with a final and pretty sobering question. We are on a path back to a world that looks a lot like the one before antibiotics, a world where a simple cut or a routine infection could once again become fatal. So the question for all of us is, looking at that future, what are we going to wish we had done differently today?